we were talking about Hamilton's equations and canonical transformations. If you remember, the main ideas were that there are these transformations you could do where the Q's and the P's are kind of on an equal footing. In some sense, they can vary independently, which is unlike what you could do with Lagrangians, where you just have the configuration variables, the Q's. And there's all different kinds of ways you could do these transformations to preserve Hamiltonian structure. You have to preserve the Hamiltonian structure of the equations, meaning you need to have Q dot equals partial H partial P, and P dot equals negative partial H partial Q for all of the variables. But that's still a very large set of transformations, much bigger than you get with just Lagrangians. And a technique to find them is called generating functions. But we kind of need to back up. Well, not back up. We need to look at some other things to even understand where the generating functions come from. So for this lecture, I'm going to talk about variational principles of mechanics. And this will get us into, where does the generating function come from? Plus, it'll give some additional insight into where do the equations of motions from mechanics come from. In some sense, this is as deep or as far as it could go. It's the best we can do. These are the variational principles of mechanics. I think when I started out describing the Lagrangian and the Hamiltonian, I said, well, one of the benefits of the Lagrangian is it comes from a variational principle. It's not quite true that that's only true on the Lagrangian side. You can get the Hamiltonian equations also from a variational principle. But we're going to start with the Lagrangian because that's kind of the easiest. And I've put some readings. There's a really good one by Feynman where he kind of does it in an intuitive way. Richard Feynman, who was a famous Nobel Prize winning physicist. But what this is often called, what we often start with, is we call it the principle of least action. PLA. It's sometimes called, because Hamilton came up with it, Hamilton's principle. And confusingly, Hamilton's principle relates to the Lagrangian. Go figure. So if we have a Lagrangian, and typically it's kinetic minus potential for a system, it doesn't have to be. There are systems like interacting vortices where you could write a Lagrangian that isn't kinetic minus potential. It's just an interacting function. We'll just start with something that's only 1D, and I'll use a variable x. So if we have a Lagrangian, and I won't have it depend on time. You could have a Lagrangian that depends on time, but let's just say we have a Lagrangian that comes from a 1 degree of freedom situation, and our variable is x. What is the action in this principle of least action? Well, the action is an integral. So it's sometimes written this way, s bracket of x of t. And it's the integral over time, so say between 2 times t1 to t2 of the Lagrangian. So it's like you take in a function x and you calculate an integral of the Lagrangian for that function. If you think if I have a curve x, let me just draw it, schematic between 2 times, and I've got some starting point and final point. There will be some curve, right? This is x. So that's x of t. And from x of t, since you know where it is in time, you could calculate x dot, and you could populate this function L and calculate this integral. And what's it going to have units of? It's going to have units of, L has units of energy. So this is energy times time. But S is definitely an integral. It's sometimes called a functional. I don't know if I'll use that language. So if this was a 1 degree of freedom case of kinetic minus potential, then the Lagrangian would be like 1/2 m velocity minus some potential energy that just depends on x. Here's what the principle of least action states. It says that the x of t, so the function that minimizes, that's where the least comes in, that minimizes the action integral s of x is the actual physical trajectory. Meaning there could be other paths, other x's, and maybe they do some other stuff. But we could, for this orange path, I could calculate the integral. For some other path, I could calculate the integral. But there is some particular path that will minimize this integral, and the claim is that is the actual physical trajectory taken by, physics. So this is I think of it as a global principle because it's taking in the entirety of a trajectory. So to go from point A to point B, we want point A to point B. What's the actual physical trajectory that does that? It's the one that minimizes this integral. So you could think of it this way. The minimum of all the trajectories of S is going to be the true physical trajectory, and vice versa. The true physical trajectory be the one that minimizes that. This principle is global because it takes into account the entire trajectory. But what if we want to know, I'm just at some point along the trajectory, maybe here, somewhere between point A and B, and I just want to know infinitesimally, what's the true trajectory doing? Well, infinitesimally means there's going to be differential equations involved. So the local principle that comes from this global principle that gives rise to the true physical trajectory, and maybe you could guess what it is, it's going to be Lagrange's equations, right? Total derivative partial L partial x dot minus partial L partial x equals 0. So the global principle is this principle of least action, but if you work out its implications locally, and I mean like locally in time and in space, this is the local principle, the Lagrange's equations. Okay, so that's the big picture of this idea of the main variational principle of mechanics. It's this principle of least action. Now, we need some tools to show this. I'm going to first give a kind of hand-wavy physicsy explanation. Part of how the machinery works is you have to assume there is a true physical trajectory out there. So here's the hand-wavy explanation. So if you haven't heard what what it means, I'm just sort of waving my hands and you can't, there's some sleight of hand going on, like a magician. So what's the hand-wavy explanation? Unfortunately, all of the explanations, I think, start with this thing, which is, let's suppose we have the actual trajectory x. This is the one that minimizes the integral. So we have that. And let me sketch it. It's always nice to have a little bit of a sketch. So this is time, this is x. And we've got some true trajectory. I don't know what it is, but it's there. And then we vary the trajectory. So we say, we start with the true one and then we vary it. What does that mean? We go from x to x plus, I'll call the variation delta x. So this is a small variation. It's a continuous function of time. So delta x is a small variation at each time. So what do I mean? If I've got this delta x, I'll draw it down here. Delta x will be something that Maybe it goes up and then down and then up again. It could be any arbitrary function. I'm just sort of drawing something and drawing arrows. I'm going to add this delta x to x up here. And then I'll draw the result in green. It'll be just sort of trying to add these two together. And I'll get something that goes up, goes down below the true one, and then is above the true one. So that's what this green thing is. The green thing is x plus delta x as a function of time. So this is the varied path. And delta x, the variation, is actually, like I said, it's arbitrary, and it's called the variation. All right, so when we do that, then what we've calculated for s, for x, now goes to s plus delta s. Okay. And we want to calculate what delta s will be. And at the very last step, we'll say delta s equals 0. Delta s equals 0 for s at a minimum. And that will give us the differential equations for the true path. So there's something else we have to do here, which is that when x goes to x plus delta x, the time derivative of x also goes to time derivative of x plus time derivative of delta x. And we'll deal with it later. What is the time derivative of delta x? What is s? That's just what we've written up above. Just for concreteness, we'll use that Lagrangian of kinetic minus potential. So this is the integral of 1/2 mass x dot squared minus the potential integrated over time. So what is s plus delta s? Well, what we do is we now write the integral, but every place we have x, we put in x plus delta x. Every place we have x dot, we put x dot plus delta x dot. So this integral, maybe if I write it here, put a square bracket around that. We put some square brackets around here. This will be 1/2 m x dot plus delta x dot, that whole thing squared, minus potential of x plus delta x. Right, this is what we would get as we vary the path. We're going to get s at its minimum plus whatever this variation is, and it would be this integral. But now we're going to expand out this right-hand side. We're going to expand out the integral and keep just the first order terms in the variation. Okay. You will expand this, keeping only first order variations. So things that are first order in the variation. So if I get like delta x squared or delta x dot squared, I'm going to say that's very small and I throw it out. So what do we need for this? Well, there's this prominent x dot plus delta x dot squared. Expanding that out, we get x dot squared plus 2 x dot delta x dot plus delta x dot squared. I'm going to say this thing that's delta x dot squared is just, I'm going to treat it like it's 0. Right, this is a common thing when you're saying our variation is small. Variation is small. And so is delta x dot. Okay, so we'll ignore things that are square of small terms. What about potential of x plus delta x? Well, now we use Taylor series expansion. So this is going to be v at x plus partial v partial x evaluated along the true path and times delta x. And the next higher order term in the Taylor series expansion is going to be something that's of order delta x squared. So we will ignore it, just like above. Ignore, okay? So what do we get for s plus delta s? Right, so s plus delta s equals I've expanded some of this stuff out, right? So we'll have 1/2 m x dot squared plus 1/2 m 2x dot delta x dot. And then the next thing in that kind of kinetic energy is I ignore it. Then what? Minus, right, from up here, minus v of x minus partial v partial x. And I'll just say, yeah, this is along true trajectory, delta x. And everything else is small, so we're only keeping things to first order. Here's dt. All right, now there's some things we can notice here. If I kind of scoot up a little bit, what was s up here? It was 1/2 that minus v, and I've got the same terms here, 1/2 m x dot squared minus v. So it looks like I have already in here s, and then I have some other things. So let me just collect those. This 1/2 and this 2. So those things cancel. And I've got an integral t1 to t2 m x dot delta x dot minus partial v partial x evaluated along the true trajectory delta x dt. So I have this thing. If this, right, from the left-hand side, this is s plus delta s. Well, I have s here. So in some sense, what am I left with? This thing is delta s. This is delta s. So we have an expression for the induced variation in the action due to the variation in the path. So we have an induced variation in the action due to a variation in the path. We don't yet have this exactly in the form we want, but let me just give some idea of what the next steps are. Delta s equals 0 for s at a minimum. You might say, why is that? So I'll try to give some intuition. Also, what we're going to try to do is write this delta s. You see how right now it's got x dot and then delta x dot. We're going to try to write the whole thing as some integral over time that's going to be multiplied by delta x. And then because delta x was arbitrary, the thing in the parentheses will be 0. Always has to be 0. So that's what we're building towards. Okay, so here's the intuition for why delta s has to be 0 for s at a minimum. Intuition from the usual calculus. This sort of suggests I'm going to teach you some other weird calculus. There's something called the calculus of variations. So here's the intuition. When you've got a function, let's call it y of x, and it has a minimum, any kind of smooth function that has a minimum. Let's say here's the minimum. It's right there. Let's call that x star. Well, what's the condition for a minimum? The condition for a minimum of y as a function of x, so the usual calculus, is, well, we should all know it. You take the derivative of y with respect to x, you set it equal to 0. Another way to put that would be if we know where the minimum is, and then we do a variation, x star plus dx, that'll lead to dy equals 0. So to first order, variations in dx lead to no change. And why is that? It's because think of what this curve has to look like near a minimum. Near a minimum, it has to be quadratic. It's kind of the idea. Near a minimum, y of x is quadratic, right? It looks locally like a parabola. So looking locally like a parabola means it doesn't look locally like a line. It looks locally like a parabola. So you get this. Okay, so the same thing holds when we're looking at this. Kind of have to make a leap of logic here, but now here x, kind of sketching for the y-axis, this is the space of all possible curves. And for each of the curves, we can calculate what S is. So, you know, you could do this piece by piece, and then just, you know, you're going to have something. So this function S, the axis doesn't look linear, like it's the space of all possible curves, but there will be a minimum. We're assuming from the beginning that there is a minimum. And so there will be some special trajectory that we're saying is the true trajectory. Is the true path. And that, you know, has some kind of S min value. So as we now, instead of the real normal calculus, now we're using this weird delta stuff. So x goes to x plus delta x. And so that means that the minimum is at where we have first order variations in S are 0. So hopefully that helps. Okay. So that's why this condition up here in the upper left is true. Now what? Now we need to do this part. We do that by doing integration by parts. So one thing I sketched up there but didn't quite say, the variation delta x vanishes at the endpoints. That means that delta x at time t1 is 0, and delta x at time t2 is 0. So that first order variation thing that I sketched, it has to go to 0 at those endpoints. And that will have implications, because now that we've got some kind of boundary conditions, we can use integration by parts. And what do we get? Integration by parts for that one term that had, it was m x dot delta x dot dt. Well, using integration by parts, this becomes m x dot delta x dot, sorry, delta x. And then the way integration by parts it works is it's like you move a derivative to the other thing. So we get integral m x double dot delta x dt, right, from t1 to t2. So that's what we get. And now we could put this into our formula for delta s. So delta s equals integral, and I'm going to pull out delta x. So we get minus m x double dot minus v all times delta x, which is a function of time, dt. And the condition for a minimum is that this equals 0. And this function is arbitrary. I guess I wrote it in blue. So this variation function is arbitrary. So it's not like necessarily equal to 0. So if that's not necessarily equal to 0, the only way this entire integral could be equal to 0 is for the thing in the brackets, the square brackets, to be equal to 0. So minus mx double dot minus vx equals 0. Or another way to put this is mass times acceleration equals, oh, sorry, I messed up somewhere up here. This wasn't v, this was partial v. Partial v, partial x. So this is partial v, partial x. This is minus partial v, partial x. And then maybe now you'll recognize it as, this is Newton's second law. We've got a potential, a force that comes from a potential energy. All right. And that's the same when you have a potential energy like that, then that's the same as Lagrange's equations, same as we would get. So the true physical path, this is weird to me, and hopefully it'll be weird to you, or maybe you've got some tremendous insight. Right, going from, if you know that, you know, a ball or something, a particle or a physical system goes from point A to point B, there's going to be some true path, and any variation of that path is going to give some larger value of the integral, even if it's the straight line in at least xt space. So the true path, which globally minimizes that integral, can locally be described by Newton's second law. Globally minimizes that. It's the integral of the Lagrangian over time can locally be described by Newton's second law, which is also a form of Lagrange's equations, right? So you get a differential equation, and that's kind of weird. All right. So we just did, for just understanding here, we did this with 1 degree of freedom. But this works for arbitrary Lagrangians. So not just t minus v, any kind of L, in n degrees of freedom. So that means that if you work out what is delta S equals 0, and here the variations in each of the degrees of freedom need to be independent of one another. They're not all connected. So the first order variation equaling 0 is equivalent. So this global principle is equivalent to the local differential equation principle. Now I'm using the Q's like we have usually seen. You get this in each of the degrees of freedom. So for each index I. So again, this is global. The global, what did I call it? Principle of least action. And this is local. And it's sometimes called, instead of the Lagrange equations, mathematicians will call them Euler-Lagrange's equations. Okay. And you might say, well, why are we calling it the principle of least action? This first order variation works not just if you have a minimum, it would also work if you have a maximum or even an inflection point. So if we were to be more correct, we would say it's just the principle of extremum action, but that doesn't have quite the same ring to it. And you might ask me, well, do all physical systems actually minimize the action? I don't really know the answer. Maybe there's something to maximize it. I don't know. But then you just put a minus sign and a maximum becomes a minimum. Are there inflection points? I don't know. Like, does it mean something if they do? I don't know. All right, so now I'm going to give you some techniques in the calculus of variations. So it's less hand wavy. It's more math. And just like before, I'll just say, let's do a 1D problem. And then, oh, hey, this generalizes to N. Sort of a whirlwind tour through techniques in the calculus of variations. I think this is from Goldstein. I don't know exactly where, but that book is pretty good. So we're just going to consider a 1D problem and then go from there. Because if you can get this in 1D, then you can do it in N. So we're going to call our 1D dependent variable y and the independent variable x. So this just puts it in a kind of a mathy language where, you know, with an analogy with mechanics, x is playing the role of time. Okay. Time is the independent variable. We're always looking at how things evolve in time. So we've got that, we've got a curve. And I don't know what it does. Here's an example, y of x. And it's got an initial point, x1, y1, and then a final point at time, or at x2, the value is y2. And just to write the derivative in a compact way, I'm going to write that y dot, instead of y prime, I'm writing it as y dot, but this will mean derivative of y with respect to x. So if I have a curve y of x, I can at each point calculate its derivative. So I'm assuming y is smooth enough, I can do that. All right, and what are we going to want? We want the path y of x from y at x1 equals y1 to y at x2 equals y2, which minimizes, or actually more generally just extremizes, the integral. So we're going to write an integral. The integral, we'll write it in a similar way, but I'll use the symbol I instead of S. I is a functional, meaning it takes in the function y of x and it spits out a number. And the way it spits out that number is through taking the integral. So we integrate from x1 to x2, and I'll write the integrand as some function phi, capital phi. That will be a function of y dot, which is just dy dx. And then maybe I'll put a semicolon to say it could possibly be a function of the independent variable x. But we are integrating over that independent variable as well. So this is the function, this is the integrand. Okay. Now, yeah, the way I think of it is you're looking at, you take some curve from the space of all possible curves, because it's infinite dimensional. If all we have to do is we're sort of pinning a curve down at 2 points, now draw curves that are functions connecting those two. It's an infinite number of. We take that, we calculate an integral of that, you know, curve, and we get a number. Now we want to take this infinite dimensional problem, right? Because space of all possible curves is infinite dimensional. So we might just throw up our hands and give up, but we won't. So we take this infinite dimensional problem and put it into a form that where it looks like the usual finite dimensional calculus. So it's kind of a cheat to say, oh, this is a new kind of calculus. We're going to take something and just put it into the usual calculus. And how are we going to do that? We're going to use this idea of, we've got, just like I kind of sketched up above, we've got I, and then we have this space of all possible curves along this axis here. But we're going to label the curves with just one scalar value. So we label curves with a continuous index, and we'll call it epsilon, where epsilon equals 0 is the correct path. That is the one that extremizes the integral I. And I say extremizes because that means maximum, minimum, or inflection, but it's probably useful to think of a minimum. So it's like at this space of all possible curves, there is some, we've got epsilon, and here's epsilon equals 0. We have some special point, and anything else is going to be higher. So this axis is actually the epsilon axis. So we write the curves, y, x, and then this index after the semicolon. So this equals x with index 0, meaning the true path, the correct path, the unknown correct path, plus a small epsilon times the varied path, where y is just some variation. Okay, so here is the unknown, currently unknown. We're going to try to find some conditions for it. This is the unknown correct path. And then this is a small variation. Again, arbitrary, small variation. And like before, we're saying that the endpoints are fixed. So that that means delta y at x1 and delta y at x2 are both 0, because we're going to have to do an integration by parts. So what do we get for I? The integral takes in now y, and for using this continuous index epsilon, we'll just describe this as, this is I now as a function of only epsilon. So now I is just a function of a scalar epsilon. Looks like the usual calculus. And we can write the integrand this way. There's that. It's a function of also the derivative of y with respect to x, and possibly x itself. Okay, so now we've got this. So I is just a function of the scalar epsilon. So then the extremum is like the usual calculus. d epsilon evaluated at epsilon equals 0, because we're saying that's the correct path, equals 0. So usual calculus now, yay. Got this curve. And there's a minimum. Here's epsilon equals 0. So again, it's going to look kind of parabolic. So this is where the derivative vanishes. Di d epsilon equals 0. And now we just have to take derivatives. So we've got this function I is a function of epsilon. Now we're just going to take derivatives of it and set epsilon equal to 0, and then set di d epsilon equal to 0. So this is what we're starting with. And we've got this up here to work with. We've got this unknown integrand function, but that's okay. We can take derivatives of it. So we're going to have to differentiate under the integral sign, but that's not the end of the world. So let's just power through this. So di d epsilon, where I is up there, integrate under the integral sign. We get what? Partial phi, partial y, partial epsilon. I should probably leave some things there. Plus partial phi, partial y dot. So y dot gets treated as a separate variable for the purposes of this integral. Right, because it also depends on epsilon. There's an epsilon there. Partial y dot, partial epsilon. And x does not depend on epsilon, so we don't have to take any partial of with respect to that. Dx. Okay, well, partial y, partial epsilon, we can get that from how we've defined y up here. Epsilon is only there. So what do we get? We get partial y, partial epsilon is actually delta y. We'll leave this thing, second one, for now. Maybe we'll figure something out about it. Okay, partial y dot partial epsilon equals what? Partial epsilon. And what is y? It's dy dx, or we could just as easily write it as partial y partial x, because we've sort of written that y is now a function of x and epsilon. And we're assuming this is smooth enough, we could rearrange the order of the derivatives. So this is partial x of partial y partial epsilon. Oh, that's cool, because we just said up above what that is. This is just delta y. So then this is partial with respect to x of delta y. And then what? So that then goes into here, and we'll have to do integration by parts. You might be, okay, why is that? At the end of the day, we're going to want something where we want di d epsilon to be some integral of stuff times delta y, which is arbitrary dx. And because delta y is arbitrary, the thing in the parentheses has to be 0. That's just sort of the way things work when you do calculus of variations or any of these variational principles. That's what you're trying to do. So we have to rewrite this term so that it's something times delta y. So we got to do integration by parts. So if we get that term in terms of its integral form, partial phi, partial y dot, partial epsilon dx. But let me just write what that is. This is partial x of delta y. We want to move that partial x over to the other thing. So we do integration by parts. And what do we get? We get this times delta y evaluated from x1 to x2 minus, yeah, I put t over here. This is not t. This is x. doing everything in x. Minus what? x1 to x2 partial x partial v partial y dot times delta y dx. Ooh, okay, but what is this? This is going to be 0 because delta y of x2 and delta y of x1 are both 0. So this thing is 0. So we pick up nothing from that. And now we could write d epsilon equals, and I'll use curly brackets. Kind of running out of brackets. x1 to x2. Now maybe I'll use square. This is partial v partial y. I'm pulling out an overall delta y. So delta y. This is minus partial with respect to x of partial v dot. Partial y dot. Okay, and this is all evaluated at epsilon equals 0. So maybe we just remind ourselves of that. And right, this thing, d epsilon needs to equal 0 for us to be at an extremum, right? Kind of that's this. What's going on here? So because delta y is arbitrary, since this is arbitrary, then the thing in the square brackets is equal to 0. That's the only way this integral will always equal 0. So this is 0. And if we now just multiply it by -1, it looks, you multiply something by -1, it's still equal to 0. It just looks more familiar, right? We get partial with respect to x of, and this could be now considered the true derivative. So dx partial v partial y dot minus partial v partial y equals 0. And that should look very familiar. It looks like the Lagrange's equations, but this is general. We didn't say anything about mechanics at any point. We didn't say anything about kinetic energy. This is just something that comes from the calculus of variations. So it's just math. And when it does come from just math, we call it the Euler-Lagrange equations. So some people will refer to Euler-Lagrange and the Lagrange's equations of mechanics interchangeably. But in some sense, this is, not in some sense, this really is general. No mention of mechanics, which means it could be used to solve a wide range of problems, not just from mechanics. So if you're thinking, okay, how to apply to mechanics? For mechanics, instead of phi, you use L, the Lagrangian. Instead of using x as your independent variable, you use time, t. And instead of y as the dependent variable, you use a generalized coordinate, q. And then this just becomes exactly d by dt, partial L, partial q dot, minus partial L, partial q equals 0. You get Lagrange's equations of mechanics. But this is way more general, so you could use it to solve a variety of problems. Anything that could be written as you need to integrate to find what the path is. So for example, maybe you've heard of geodesic problems. Like one of them is, say in the flat plane, I have 2 points. What is the shortest path between those 2 points? Well, you could write that as an integral over the arc length. And what you'll find is that in the plane, the shortest path between 2 points is a straight line. But then you could do this as, well, what's the shortest path on some other curvy shape? So you could find other things. There's also the Brachistochrone problem. That's sort of a famous one. And that one may be worth mentioning. It's kind of cool. And you might say, well, but this seems to be related to mechanics. Yeah, but we're not, not really. So some people pronounce it all weird. Brachistochrone problem. And the idea here is if you were to, we'll have X, and then we'll measure Y going downward. If I release a mass or a very tiny ball, so don't worry about the rolling without sliving, something, I want to create a path that takes me from this point 1 to some other point 2. Gravity is present. So what is the path that goes the fastest from rest at point 1 to point 2? Goes the fastest, I mean shortest time from rest at point 1 to point 2. You don't have to be at rest at point 2, you just have to get there. So this could be written as minimized time from 1 to 2. And just to give you an idea, like here's a path, it's not maybe the best. And I've got something that's going to be going along that path. Well, you might say, well, hold on. I think I know. Maybe a straight line is the best path. Or maybe no, maybe I want to fall really quickly and then get there. It's not obvious what is going to do this. If we minimize the time, we could write it this way. The time to go from point 1 to point 2, we'll write it as a functional. It takes in this function, y of x, and we're integrating from point 1 to point 2, just the time. And what is that time? We could write this as 1 to 2. For each little arc length, each little tiny bit of arc length, the time it takes, the differential time would be arc length divided by the velocity along that path. And you could rewrite this as some function, some integrand dx, right? So v is change in arc length time. That's how we went from there to there. So there's some integrand that'll be a function of y dot, and x, and you can get the answer. The answer is this. I mean, this is a really common homework problem for calculus of variations. The answer is a cycloid curve, or some people just call it the Brachistochrone. And it's cool to see a demonstration of it. So Vsauce, the channel Vsauce, he has a really cool demonstration where he partnered with one of the Mythbuster guys. So this is their demo. You can see they've got a setup here. They've rigged something up with plexiglass. They're trying to go from point A near, the guy's hand up there to the bottom. And they've got a straight line path. And then this thing that falls quickly. And then the thing in the middle is this Brachistochrone curve. So they've got something that releases 3 balls from rest, and they're going to try to see what gets there first.
All right, you ready?
Right, I'm ready.
Count it in.
3, 2, 1, go. Yeah.
Same results?
Same result.
Hard to see.
1, 2,
But
3.
these are so close, it's hard to tell.
So now they do slow-mo. You can clearly see.
Well, we're answering the main question, which
You could see it. Let's show it again. So they release from rest. Some cool music playing. And you could see that middle one, which is sort of the compromise between straight line, and then the first one gets a lot of speed quickly, the one that is really steep, but it doesn't get there first. So the Brachistochrone has this optimal compromise between straight line and having speed, and building up speed due to constant acceleration. That's the Brachistochrone curve. There's all kinds of other applications of the calculus of variations. Maybe you've heard of spline curves, right? Where you have data points. Spline curves come from a calculus of variations thing, where if you have a bunch of points, let's say this is X, this is Y, and you've got a bunch of data points and you're trying to fit a curve through it, you don't want to, let's say, you don't want to use just some kind of lame straight line interpolation. You think there's some kind of smooth curve. So you could find a curve that minimizes curvature and goes through these points. So the thing that minimizes curvature and goes through these points, I don't know, it's going to be something like that. Often you want some kind of smooth curve from data points for maybe some simulation. But so splines, often called cubic splines. It turns out the cubic part comes out of your analysis. You need things that are third order polynomials to get this smooth fitting. So the cubic splines minimize, I think it's curvature. And this would be a different type of problem because it's calculus of variation with constraints. You can't just have a curve. The curve has to pass through these particular points. And that's what's happening behind the scenes whenever you use spline in, say, MATLAB or something. All right. What we'll do next time is talk about how there's kind of this symmetry to Lagrange's equations, which is that if you have a Lagrangian, you could then write an L prime just means this is a different Lagrangian where I've said L. The new Lagrangian is L plus some total derivative, and it doesn't change my equations of motion. Both L and L prime have the same equations of motion. And this can be shocking to people if you think that you are finding the Lagrangian for your system. No, there's this arbitrariness. It's a kind of symmetry. You could add any total derivative to your Lagrangian. And here, I mean, f is a function of the q's and possibly time. And you'll get the same equation of motion. If I have a system and I just sort of add a total derivative, then maybe I've wasted my time. So here's an example of a particle seen in a frame rotating with an angular velocity omega. You could get a Lagrangian for this system. It'll be 1/2 m x dot squared plus y dot squared plus m omega x y dot minus y x dot plus 1/2 m omega squared x squared plus y squared. So this is a particle seen in a rotating frame. It's like it's a free particle, so there's no potential, there's no real potential energy. There's just stuff related to rotation. But we can notice, you can get some Lagrange's equations from this, but you could notice that there is a total derivative here. So we notice that x y dot minus y x dot is the same as minus 2y x dot plus a total derivative of x times y. So this would then be our function f. So the equations of motion, or Lagrange's equations from L, are the same as from, we defined some new L prime that differs just by that total derivative. 1/2 m x dot squared plus y dot squared. That part's the same, but then we get minus 2m omega y x dot plus, and then the last term is the same as well. These are not the same Lagrangian, but they do have the same equations of motion because they differ only by a total derivative. What seems like a side comment when people talk about Lagrangians ends up being really important for Hamiltonians, because we're going to base the possible, a tool for finding canonical transformations through this arbitrary function f. And so that's what we'll do next time. But I think that's it for now.